In today's lesson, we are going to be looking at finding side lengths using right angle trig. So this should be a review from last year in grade 10. You would have finished off the year looking at trigonometry. So we're going to kind of go over some of the stuff that you looked at last year as well as some new things. So if you remember from last year, labeling a right angle triangle is very important when we're dealing with right angle trig. So we need to make sure that we label our triangle properly before we get into using any of the formulas. Now, labeling the right angle triangle focuses on the sides in relation to sometimes the right angle or sometimes in relation to an angle that we're given. Right? But right angle trig focuses on a right angle triangle. So we need to make sure that we have our right angle in our triangle. So usually, again, it's indicated with that little square that indicates that we have a right angle. Now, there are three sides that we need to label or be able to label in our triangle. We have the hypotenuse, the opposite, and adjacent. So the hypotenuse is always going to be across from our right angle. And it is also the longest side. So in some cases, it might be easy to tell which side of the triangle or the right of the triangle is the hypotenuse because it's going to be the longest side. In some cases, it may not, depending on how the triangle is rotated, but you can always assume that it is going to be across from the 90-degree angle. The other sides, the opposite and the adjacent, these could be in either location. It could be either on the bottom or on the side for either of the two. What we do need, though, in order to label the opposite and the hypotenuse is an unknown angle. So this little symbol here looks kind of like an 8, or it's like a circle with kind of like a little swirl at the top. This is going to be what we call theta. And theta just represents an angle. In this case, it's going to be an unknown angle, but we are going to use it as our reference. So when we're labeling a right angle triangle, aside from the hypotenuse, the other two sides are going to be based off of our reference angle. Now, this reference angle could be unknown like it is here, or it could be a known angle. So in some cases, we're told what the measure is. Once we've labeled our reference angle, or once we know what our reference angle is, our opposite, let me change colors here. Our opposite is going to be across from our reference angle, or opposite of the angle. So opposite of our angle is across from our unknown. And then our adjacent is the last remaining side. You could also think, well, the word adjacent means beside, and the adjacent side is beside our reference angle. So knowing how to label these three sides is very important, and it should always be your first step when using right angle trig, because we need to know what our sides are to help us figure out what trig ratio to use. Now, with right angle triangles, there are three primary trig ratios: sine, cos, and tan, and they're different ratios, or they use different pairs of sides. For our sine ratio, we have opposite and hypotenuse. For cosine, we have adjacent and hypotenuse, and for tan, we have opposite and adjacent. So for each different ratio, we use a different set of sides. To help you use the ratio, sometimes you can remember SOHCAHTOA. SOHCAHTOA is just an acronym. Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. And tan is opposite over adjacent. So just a little acronym to help you remember what sides you're dealing with each ratio. And it also tells you the order. So sine opposite over hypotenuse. So the second two letters are going to represent the sides that you're dealing with. The second letter is going to be on top. The third letter is going to be on the bottom. You also have your formulas up here, which you'll get anyways, so you don't need to worry about that if you don't remember the acronym. So now we're going to look at a couple examples dealing with each ratio. And we're going to look at a couple of different, or two scenarios in each. The first one we're going to deal with is the sine ratio. Zoom in here so we focus on this one. So again, I am saying that it's going to be the sine ratio, but let's label our triangle just to make sure. So we have our hypotenuse h, because it's across from our 90-degree angle. We have our reference angle here. So this 38 is our reference. So we're going to use that to label our other sides, which means that 18 represents the opposite, and then the other side is the adjacent. I'm only dealing with the opposite and the hypotenuse. And what I mean by dealing with them, those are the only ones that I have information for that I'm going to be using. I'm using the opposite because I know what the side length is, and I'm using the hypotenuse because I'm trying to find that side. So because we're dealing with O and H, that means we are going to be using our sine ratio. So sine of an angle is equal to the opposite divided by the hypotenuse. Now I'm going to fill in our missing information or the information that we're given. So again, theta, this little symbol, is our angle. So sine of 38 is equal to the opposite, which is 18, over the hypotenuse, which is x. Now we could kind of go the long way. If I want to solve for x, right now it's on the bottom, so I do need to bring this x up. Just when we're dealing with, rearranging equations. So we have x times sine 38 is equal to 18. Now sine of 38 is a number on its own. So if I want to get x by itself, right now it's being multiplied by sine 38, or x times a number. This sine 38 is now going to move to the other side, and it's going to become division. So x equals 18 divided by sine 38. And we get x is equal to 18 divided by sine 38. We get a side length of 29.2. So that is our unknown side length, or our missing side length. Now you could look at that and you can kind of, one indicator that tells us that this probably is the right angle or a good answer is the fact that it's bigger than the opposite side that we're using. Right, remember, we're trying to find x or the hypotenuse, so it should be the biggest side. 29.2 is bigger than 18, so at least that makes sense as an answer. If we got a number that was smaller, we might have to relook or redo our calculations. Looking at another example for sine, again, we're going to go through the whole process. We're going to label our sides across from the right angle. Across from our right angle. Wait, why is it? Pen does not want to work. So across from our right angle, we have our hypotenuse. We have our reference angle. Across from our reference angle is our opposite. And then the last side is our adjacent. Again, the two sides we're going to be dealing with are O and H. We're looking for the opposite, and we're given the hypotenuse. So because it's O and H, it's going to be sine, or the sine ratio. So sine theta equals the opposite over hypotenuse. I'm going to plug in the information that I'm given. So sine of an theta, or sine of our angle, is 18, is equal to the opposite, which is x, over the hypotenuse, which is 19. Now I want to get x by itself. I'm trying to solve this equation for x. So So to get x by itself, I have to move the 19 over. When I move 19 over, I bring it up. It's division on one side, it becomes multiplication on the other. So 19 times sine 18 is equal to x. This just becomes a calculation. 19 times sine 18. I get 5.9 is equal to x. So that unknown side, that opposite, is the unknown side is 5.9. Again, we can kind of take a look at our side lengths and try to see if our answer looks good. In this case, it is smaller than the hypotenuse, so just by looking at it, we can say that, yep, you know what, that does look good, that makes sense. It should be smaller. So we know we didn't do anything too wrong. Now that's the sine ratio. The next one we're going to look at is the cosine ratio. Now cosine is cosine theta equals the adjacent over hypotenuse. So the two sides we're going to be dealing with when we're looking at a right triangle is the adjacent and the hypotenuse. So in one example, again, I'm going to label my sides. Across from the 90-degree angle, I have the hypotenuse. I have my reference angle. Across from my reference angle is my opposite. And the side beside it is the adjacent. Looking at what sides we have information for, we have the hypotenuse, we have the adjacent. Again, that leads us to using the cosine ratio. So cosine of theta equals the adjacent over the hypotenuse. Plug in the information we know. Cosine of 58. Looks like a 5. So cosine of 58 is equal to 20 over x. And now I need to solve my equation. I'm trying to solve this equation to get x by itself. X is on the bottom right now. I don't want it there. I'm going to bring it up. We're seeing a similar kind of pattern or similar steps to what we just did with sine. So bring the x up. It's now x times cosine 58. I want to get x by itself, so I need to move the cosine 58 over. In this case, now it's going to become division. So 20 divided by cosine 58. And this is now just a calculation because I can divide 20 by cosine 58 and get 37.7. Cosine 58 is just a number. Depending on your calculator, you may need to calculate what cosine 58 is first and then divide it by 20. If you do have one of those calculators, I would highly recommend getting a good scientific calculator. You can easily find them on Amazon or Staples for around $12, $12 to $14. There are some decent ones that allow you to see everything you're typing in, which makes it a lot easier when solving or doing these calculations. But again, we calculated for the hypotenuse using the cosine ratio. Looking at our answer, it seems to be reasonable because it is larger than the side lengths we're using. And again, when we're trying to find the hypotenuse, it should be bigger, or the biggest side. Another example for the cosine ratio, again, I'm going to label all my sides first. So I have the hypotenuse because it's across from the 90-degree angle. I have my reference angle. So this long side over here is the opposite. That leaves the unknown, or x, with the adjacent. And again, a and h are the two sides we're dealing with, which tells us cosine. So cosine of an angle is equal to the adjacent over hypotenuse. Fill in our information after we know the ratio. So cosine of 69 is equal to x over 13. Now that I've plugged everything in, I want to solve my equation, so I need to rearrange for x. The 13 needs to come up. It becomes 13 times cosine 69 equals x. We do that calculation and we get 4.7 is equal to x, which is our unknown side. Again, at first glance, it does look reasonable because it is smaller than the hypotenuse. Now, before we get into the tangent ratio, let's go back and take a look at these two, or at the sine and the cosine ratios that we just looked at. Just by first glance, if you look, and let me make one small adjustment here. If you look at the two sets, the sine ratio on top up here, the cosine ratio on the bottom here. If we look at each side, the first two examples for both, the second two examples for both, it looks very similar. Right? The steps seem to be almost identical. The only difference is the ratio that we're using with. So maybe that might help us when we go through and do the tangent ratio. So if I'm going to use the tangent ratio, again, the first thing we want to do is label our sides. So again, by the end of this, you should be very comfortable with labeling. So across from the right angle is the hypotenuse. I have my reference angle of 71. So across from that is the opposite. And then I have the adjacent with the unknown measurement. The two sides we're dealing with, I'm dealing with the opposite and the adjacent now. I'm not dealing with the hypotenuse. I'm dealing with the opposite because I know that measurement, and I'm dealing with the adjacent because I'm trying to find that. So my equation has to have an A in it. So A and O, or O and A, that means it's the tangent ratio. So tan theta, we have the formula here, is opposite over adjacent, or TOA, T-O-A. Tan is opposite over adjacent. Tan of our angle, so tan of 71 is equal to 18 divided by an unknown. And if we go back and look at the last couple ones, the setup seems to be almost identical. We're missing the piece on the bottom, or the unknown piece is on the bottom. So is there a quicker way to get to our final calculation other than going through all the steps of rearranging? Well, I'm going to go quickly and do that. See if you can kind of pick up on what we're doing. So that's the quick way of doing it. So all we're really doing is just kind of simplifying some of our steps, kind of taking out some of the rearranging because we know what the final answer is going to be. So really all we have to do is just switch the unknown on the bottom with the entire tan and an angle on the left side. So we switch the two, we get x is equal to 18 divided by tan 71. This is just a calculation, 18 divided by tan 71. And we get 6.2. So we've kind of eliminated one step to make it a little bit quicker, and we have a reasonable answer that is, I guess in this case, you kind of have to almost look at the triangle and say, does that kind of make sense? Because you can't really compare the opposite and adjacent together and say, well, oh, it should be smaller or it should be bigger. Now, I would be careful with saying, oh, 6.2, that's the adjacent. The adjacent side looks smaller than the opposite. So yeah, that makes sense, because sometimes the triangles might not be drawn to scale. Right? So you just want to be careful with that. If I look at the second example, again, I'm going to go through and label my sides. I have my hypotenuse, my reference angle. So across from that is the opposite. That leaves the adjacent. I'm going to use the O and A. Those are the two sides that I'm dealing with. O and A is tan, so tan theta equals opposite over adjacent. Tan of our angle, or 64, oops, bad 64, equals O, which is an unknown, over 11. Now, if I go back and look at the previous two examples of how we solved this or how we rearranged, Really, this one was just the one step, not really anything more we can simplify, but it does seem like whatever the bottom number of our fraction is, we're always going to be bringing that up and multiplying it with our ratio and angle. So my 11 is going to come up, and it's going to be multiplying with the tan 64. So 11 times tan 64 is equal to x. We do that calculation, and we get 22.6 is equal to x. Again, we can't really compare the opposite and the adjacent to each other and say, well, one should be bigger than the other. So here we kind of have to trust our rearranging and our calculations. So now we've gone through each ratio and we've done 2 examples of each. And really, those are the only scenarios you're going to be coming across. You're not going to have a third scenario for the different ratios, at least for finding a side length. This is pretty much the different scenarios that you're going to come across. And if we kind of scroll and look at each one, the sine, the cos, and the tan, we should see that really they're almost the exact same scenarios, at least in terms of how we solve it. Right? So whether it's the tangent ratio, the cosine, or the sine, we're seeing similar scenarios, similar steps, a similar process. The only difference is the ratio we're using and the sides we're dealing with. But once we plug in our information, they look pretty much almost identical. So to summarize, there are 2 scenarios that we're going to come across. One is the missing pieces on the top, which is what we see in the second examples, and the other is when the missing piece is on the bottom. So technically these 2 should switch to make it kind of more aesthetic, but these are our 2 scenarios. So if our missing piece is on the top of our fraction, our unknown value, our x or variable is on top of our fraction. So if we look at the second column, everything that we did over here, right? Bring the bottom up and we multiply. Bring the bottom up and we multiply. Bring the bottom up to the other side and we multiply. So anytime we have a missing piece on top, kind of a quick thing we can think of is we bring up and multiply. Right? So bring up and multiply, that's the one thing you want to be thinking of when the missing piece is on top. Now it's obviously going to be a little bit more complicated than just bring up and multiply. Like it's not exactly that, right? We still have to substitute, we have to figure out the right ratio, but in terms of solving the equation, we have to just bring up and multiply. For the other one, when the missing piece is on the bottom, right? Looking at what we did, tan 71, the x switched spots. Cosine 58 and x ended up switching spots in the end. Sine 38 and x, again, after we rearranged, ended up switching spots in the end. So when the missing piece is on the bottom, when the x is on the bottom of our fraction, we switch and multiply. So again, a little bit more involved than just switching and multiplying. We have to plug things in. We have to make sure we switch the correct pieces properly. But at least you have kind of some key phrases to kind of think about when you're going through and solving these. Right? Oh, missing piece on top, bring up and multiply. Oh, I multiplied twice, sorry. Bring missing pieces on the bottom, switch and divide. Right? So 2 different operations, for the 2 different scenarios. Right? So that's it for looking at solving for side lengths with right-angled trig. Now, again, you just want to make sure that you're comfortable labeling the sides. You do need to label the sides properly before you can use these ratios, because you need to make sure you choose the correct ratio. If you choose the different ratio, like you use cosine instead of tan, you're going to have an incorrect answer. So again, you do want to be careful and make sure you take the time to label it properly. And then once you've labeled it properly, you're going to come across 2 scenarios, either the pieces on the top, missing pieces on the top, or the missing pieces on the bottom. And then we have our 2 methods for solving, and we have examples here. So this is one of those scenarios where, or one of the cases where practicing these concepts will make it a little bit easier. So when you see a specific type, it makes it easier for you to remember what to do. So again, these are one of those things you do want to make sure that you practice.